As I mentioned before, we're just going to look at one impedance matching technique, which is single stub matching. So the scenario here basically is that we have some load impedance ZL. Of course, the inverse of load impedance is simply the load admittance YL. And because ZL is not equal to Z0, the characteristic impedance of the transmission lines, and we assume in this scenario all the transmission lines have the same characteristic impedance and thereby having the same characteristic admittance Y0. So because ZL is not equal to Z0, that means if we don't have any network included here, impedance matching network, that means we will get reflections back to the generator, which we don't want. So what we do is we include an impedance matching network, which for this scenario consists of a length of transmission line of some length little d, a design parameter. And then at the interface here, we connect a stub. In this case here, short circuit stub, but also an open circuit stub could be used as well. So we're just going to deal with the short circuit stub case. And its length, capital L, is also a design parameter. Now, first of all, we'll just define a few normalized admittances. So just to the left-hand side of this interface between the stub and the main transmission line, we want the admittance looking here to the left, looking towards the load, to be equal to 1, which of course would be an impedance match condition. We'll define Ym to be the admittance just to the right-hand side of that interface, after the stub basically, looking towards the load. And then Ys here then is the admittance at the interface looking towards the stub, into the stub, which is terminated in this short circuit. So if this scenario was on a printed circuit board, for example, this could be the top track on a PCB, and then we just have a perpendicular section along here on the top part of the PCB, drill a hole, and then put a short wire, maybe solder from the top to the bottom, and the bottom here will be the ground plane. So not at all difficult to implement on a printed circuit board. But this can also be done even with coaxial transmission line systems as well. So it's a very, very common technique. So the essential matching network here then is this stub, short circuit, and also the connecting length of transmission line between the stub and the load itself. And we have two design parameters, stub distance from the load and the stub length. Now the basic idea here is to move away from the load point, typically YL on the chart, so using the chart for admittance calculations, move away from the load point on the chart to the first point on the transmission line, at which the real part of the admittance looking towards the load, Ym at the interface, is equal to Y0, the real part. That's why I've written 1 here. Of course, associated with that point will be some value, which we just call Bm, imaginary part, which we don't know yet, but which can be got, we'll see later on from the chart. And then what we will use the stub for then is to provide the susceptance to cancel the imaginary part of Ym. Because remember, Yin by the parallel rule for admittance combination will be equal to Ym plus Ys. And of course the real imaginary parts of both sides of that equation, so to speak, must be the same. So that means Yin is just simply real number 1, which must be equal to Ym's real part, which is 1. And the real part of Ys will be 0, because all that stub is basically is a lossless transmission line terminated in a short circuit stub which has got no losses. So the input admittance into a short circuit length of lossless transmission line must be purely imaginary, as it will be also the case for an open circuit stub. So our design condition then must be that Ys must be equal to minus J times Bm. And we have to find out the length of that short circuit stub to achieve that result. Now, of course, the locus of Ym in the Smith chart will be the G equal to 1 circle, because we won't know the value of Bm yet. So that's the basic technique that we're going to have to apply, and we're going to do all the associated calculations by using the Smith chart. The essential technique we're going to use is as follows. So we first of all need to locate the point on the chart corresponding to YL. So YL here being the normalized load admittance, which of course is the load admittance divided by Y0. So we find that point, of course, by finding out the closest G circle and B circle to that point on the chart. So we can do it directly, or we could also locate the actual impedance, normalized impedance, and reflect that normalized impedance point through the center to get YL. My suggestion here really is that you work out YL first of all. And if you know ZL, of course, it's simply the inverse of the normalized load impedance. That's very simple to do. Basic complex number manipulation, and then plot that point on the chart. And that avoids cluttering up the chart too much. Now on the chart here, I've actually shown the G equal to 1 circle in blue. And then what we do is that load point then, we move it towards the generator. After all, we're moving away from the load, which means towards the generator, on a constant mod gamma circle. So remember, the magnitude of reflection coefficient does not change along a lossless transmission line. And we move that point along a constant mod gamma circle until we intersect the G equal to 1 circle. Now, of course, once we intersect the G equal to 1 circle, then of course the G value is equal to 1, but we can get the associated B value, which is basically the B value of Ym that we had in the previous slide, directly from the closest B circle to that intersection point. And the actual distance then that we've moved D, in terms of wavelength, required to move from the load point to the G equal to 1 circle, can of course be found by using an appropriate wavelength scale on the chart, whichever is suitable. Now, as I've already mentioned, that actual intersection point with the G equal to 1 circle will give Ym equal to 1, the real part, plus JB, and Bm, that imaginary part of Ym, is the closest B circle to the point, or at least a reasonable estimate. If we're in the top half of the plane, Smith chart, the B value will be positive. If we're in the bottom half of the chart, the B value, of course, will be negative. So now that we've found D and we found Bm from the chart, we need to next find out the length of the stub required, which will complete the problem. So if we go back to this interface over here, again, admittances and parallel add. So Yin is equal to Ym plus Ys. So that means that we require that the stub input normalized admittance, Ys, is equal to minus JBM. So if that is the case, then it'll certainly be the case that Yin is equal to 1. So again, to reiterate, at the stub interface, Yin is equal to Ym plus Ys. Once Bm is known, determining the stub length L can be treated as a separate problem. So the problem essentially is, what is the length L required such that the input admittance, normalized admittance that is, looking into the stub at the interface, is equal to minus J times Bm, given that we have a short circuit load up here effectively at the end of the stub. The next part of the design of the impedance matched network is to determine the length of the short circuit stub. And we can treat this part of the problem essentially separately from what we had before. Of course, we know the actual value of Bm from the previous part of the problem. So in treating the short circuit stub problem, or section of the problem, we have to determine the length L such that the input normalized admittance, which is purely susceptive of course, is equal to minus J times Bm. Now, how do we do this problem? Well, first of all, we essentially have a short circuit load here. In terms of admittance, of course, a short circuit load corresponds to admittance of infinity, which of course in terms of the Smith chart, the associated G value is equal to infinity, normalized conductance. And that's simply a single point over here in the Smith chart, which is the 0.10 over here. And then essentially what we're doing is we can imagine on the Smith chart moving towards the generator, which of course corresponds to movement in the clockwise direction on the chart. Until then, we reach a susceptance which is equal to minus Bm. So for example, if Bm had a value of 1, then in terms of the short circuit stub design, we effectively move in the clockwise direction until we intersect the B equal to minus 1 circle. Now, of course, that's on the bottom half of the plane marked plus 1. And then that distance of movement, we could work out in terms of wavelengths, either using the wavelengths towards generator scale, or indeed, if you want, the wavelengths towards the load scale. It doesn't really matter, as long as you're careful with the starting point on the wavelength scale and the end point. So we can get there for L in terms of lambda. Now, we're going to do an example on this next, but bear in mind that if we had an open circuit stub, then the essential design procedure is the same, except that in this case here, for the design of an open circuit stub, the load admittance point would be over here at the point 0 minus 1. But in essence, the design procedure is much the same. Now note here that as I mentioned before, the magnitude of the voltage reflection coefficient on a short circuit or indeed open circuit stub is equal to 1. Because any wave traveling up along here towards the load, be it open circuit or short circuit, is totally reflected. So we're going to do an example on this next.